Welcome. My name is Luca Bez. I'm a research scientist at Berkeley National Lab. As Ryan mentioned, I was planning on being in person there, but due to some unforeseen circumstances over the last couple of days, you have to listen to me remotely. I'll try not to bore you a lot. I know I'm in between you and the coffee break. So I'll share some updates we have on Drishti, especially related to the HDF5 side on the Drishti Vol connector so that we can get more information from HDF5 and feed this into the entire Drishti framework. So just to give a little bit of context of where Drishti came from, when analyzing the current IO stack, we know that there's a lot of different layers in the stack, a lot of different factors that can affect performance. We have different optimization techniques that have been proposed over the years in order to fine-tune all the knobs that we have in this layer, plus all the optimizations with their own set of knobs. So this kind of creates a very complex landscape for users, especially end users, when they're running their applications and they see that their IO performance is not the same as what they've been expecting. So what we're trying to do here is how can we make use of all the metrics, all the traces that are being collected for those applications and turn that information into something that is actually useful and meaningful to the end user. So there's still a gap between the metrics we collect and how useful they are and how they can be actually point the user into some techniques or something he can do that is under his control to optimize their application. So what we want to do with Drishti, which is going to try to tackle this problem, is to visualize characteristics, behaviors, and bottlenecks, detect some of the root causes of IO performance bottlenecks, map all the metrics that we have into this bottleneck and into actionable recommendations so the user can try, and try to provide a sort of guidance. But since we're looking at the entire scope of the IO stack, we're looking towards a cross-layer profiling exploration. So we've been working on Drishti for a while now. This is the current status. So originally we had two different tools. One of them was the DXT Explorer, which some of you might be familiar with, where we provided some interactive visualizations for Darshan DXT traces. And we had a second set of tools, which was the original Drishti version, which only provided recommendations and insights. So now everything is merged together under this Drishti umbrella, including the analysis, the interactive visualizations, and the insights and recommendations. We've also expanded the support for Drishti to ingest different sources of IO logs, not only Darshan profiling or DXT traces, but also recorder. And we've been lastly working on adding support for SCORP and tau-related metrics as well. So we're feeding all of this information into the entire Drishti ecosystem so that we can generate the visualizations and recommendations to the end users. Those two tools, especially the old Drishti part, can still be used by system admins in order to just gain an overall view of how many times different triggers that possibly indicate bad performance are being triggered in the system by different users without the visualization part or the recommendation part, but just kind of more like a monitoring part. But we also have this focus on the end users by providing this kind of visualizations and their recommendations. So to provide also a little bit of context on Darshan, Darshan I think everyone's familiar with. It's an IO profiling tool. It will collect some sort of aggregated information about the number of operations, the number of bytes that were written and read from different files during the execution, but it's not like a trace per se. There is a specific module within Darshan, which is called the DXT, the Extended Tracing Module, which will provide a more kind of fine-grained view of the IO behavior. There are some caveats, though. It will only collect POSIX and MPI operations, reads and writes. So that's the only limitation we have. There is a sample of those logs on the right side of the slide, where we have POSIX in this case, the file names, the number of operations we have there, and when did that operation specifically started and ended, included its length and offset. That being said, if we have an HDF5 application, that should be clear now that we won't have this kind of more detailed tracing information, so we're going to lose some of the visualization of the entire I/O stack that we're aiming to. And this is what the Drishti Vol connector would come in. So this kind of information that we're extracting from Darshan on the visualization part of Drishti is what allows us to generate this sort of two-facet plots. On the x-axis, we have runtime. Y-axis, we have all the ranks. And every single operation is depicted on this plot. So you can see that we have MPIO in one facet, POSIX in another. But if the application is using HDF5, as I mentioned, we don't have that information here. DXT doesn't support that. Though Darshan does support some collection of HDF5 profiling metrics, there are some caveats and restrictions that often do not make it able to, for it to be enabled by default on machines because of possibly mismatching versions between the Darshan compiled version with HDF5 and the actual HDF5 library that the user was using. So last year, when we presented the original work on Drishti, on HUG, we had a couple of comments and suggestions that we should try to explore the Vol connector to get this missing information and combine with everything that we have, everything else that we are being collected and showing on the Drishti visualization and on the recommendation side. So this is what we've done. We have a Drishti Vol connector that will collect trace-related information. It was designed to be, at least initially, work in conjunction with the DXT with the Darshan DXT, so the traces, not the profiling information, and we're feeding that into the analysis and the interactive part. The recommendation side is not a full arrow there because there's some work to be done there in order for us to enhance the recommendations based on this kind of quite grain detailed information. So what about HDF5? Just to put this on context again, what we're trying to focus when the user wants to collect everything from HDF5 side are the aspects upon which they might have some control, not something specific to the HDF5 library internals per se, but something that he can change through a specific configuration, a specific parameter on how he's reading or writing his data in HDF5. So that's the kind of scope we want to go for, and you're going to see the kind of operations we're supporting right now through the Vol connector. Also in HDF5, we know we have some internal, static, and dynamic metadata that could be of interest. Since we're creating a Vol connector, not all the operations are going to go through the Vol connector. So we're just considering in this case the dynamic metadata operations, that being the attributes, reads, and writes, to collect this additional information from the library. One thing that was a little bit of a challenge is that since we're now using two different tools, possibly in combination, like having DXT enabled, but also being able to collect this data through the Drishti Vol connector, is that the timestamps of the operation might not match. So we had to ensure that we are using the same code that Darshan uses to collect and store all the timestamps for all the operations. We've re-implemented that inside the Vol connector so that we could avoid any possible offsets coming from not being able to sync what the two tools were reporting to us. So we implemented this as a pass-through Vol connector. And this initial implementation, it does collect all the traces in memory. So there is a caveat there on the memory usage and overhead. We're going to go over that in the next couple of slides. And for now, everything else has been saved on a file per process manner. On the experiments we tested on Promoter, that was the best solution so far. We didn't add any compression, or we didn't wanted to add any additional communication to exchange the data at the end of the execution to avoid imposing communication overhead to the application. So as I mentioned, we're more interested on the file kind of related operations. This is because if we look at the information we have been collecting on the DXT side, we have reads and writes, and that's pretty much it. We don't know if we're one level up, how will that translate into the application. So other operations that are eventually won't touch the file directly, we're not capturing on the Drishti Vault connector. So for data sets, that's essentially HDF5 the dataset read and write. And for attributes, that reads and writes as well. I have a note there that dataset read can possibly touch the file if we have file spatial allocation set, so set field value and set allocation time. In combination with that, it could mean additional I/O operations, but we're not capturing that at this stage. That being said, this is what it looks like once we have fed Drishti with a regular DXT trace plus the vault connector information we collected with the Drishti vault. So besides the two facets we had for POSIX and MPIO, we have one additional facet on top with HDF5 operations. This is for an application called OpenPMD. Our initial analysis with Drishti was done using this particular application. So this is the same, but added the HDF5 vault connector information there. We can now differentiate when metadata operations are happening and when data operations are happening. So metadata, the ones that actually going to touch eventually the file. So you can see that on this left side of the plot in green, we have metadata, metadata writes. For this particular application, we have different time steps, and we're not using any collective IOs, not even from the HDF5 side. So you can see that all the layers kind of look the same. Once we observed this behavior, we got all the recommendations from the Drishti report that I'm not showing right here, and we implemented all the changes, including setting collective metadata, collective data operations on HDF5 levels so that it would be translated into the lower levels of the stack. What we have is the result on the right side of the slide. You can see a pretty much well-defined behavior for the application in between data and metadata. And we're using collective operations. And that's why we see some differences on the MPIO level to the POSIX level, where just the aggregators are actually doing the IO request. And with all of those optimizations, you can see that we went for a little bit over 5 seconds to less than 0.8 seconds. So this is one way we can use the information we're collecting to visualize the behavior application and making some of the recommended changes that Drishti will report. As I mentioned, there is some overhead, yes, but we have two caveats here. So first one is we're trying to collect information from multiple levels of the iOS stack, and we know we don't have a tool that will collect everything without additional costs, especially since we're combining two different ways of doing that. So intercepting things on the HDF5 vault connector, and we're intercepting the requests on the DXT on Darshan side as well. So there is some overhead there. Our target, once we enable this kind of visualization or this kind of analysis, is on small scale applications like exploratory runs where we're trying to debug an IO performance problem to kind of replicate the issue. We're not expecting this overhead to be paid by all the applications all the time in the system. Normally, what we have in the systems are Darshan being deployed as a profiling with negligible overhead. So you do have some aggregator counters, as I mentioned, but they won't provide you the visualizations in Drishti. You still see some of the triggers being reported by a given problem being detected. So what we're trying to do here is if you saw a problem like that, you probably want to debug and investigate further, you can rerun the application with the DXT side enabled and also the vault connector if it's an HDF5 application so that you can have the full stack information on a much lower small scale so that it's replicable without the performance overheads being that prohibitive. So to compare each line of this table, we're just adding, so the numbers would be kind of adding up to the previous layer, the baseline of the application, the previous ones that I showed with a couple of different experimentation results. For instance, we would have a median time of 7 seconds for the execution of the application. When we enable Darshan, that goes to 8 seconds, so a little bit of a 9-point 9% overhead, and we get additional 35 kilobytes of compressed data from Darshan related to the profiling information. If we enable DXT on top of that, you can see there is still some difference in time there, depending on the distribution, the number of times we repeat the experiment, but there are still some differences there. There is some overhead in time, so additionally 3% over the previous execution, but the size of the combined traces is much larger. This is because we're actually collecting every single operation that the application is doing. So the worse the application is doing, like doing tiny, several tons of tiny requests, that will mean several megabytes of information being collected there. On top of that, if we use the Drishti Vault connector, we are adding some overhead, so roughly 4% or 5%, and we're adding additional, kind of duplicating the size of the DXT. And this is because, again, we're not using any compression or aggregation to write this data at the end. So there are some overheads there, but we hope that that information is going to be valuable to end users when they are debugging and trying to understand where the problem is. So just to touch on a couple of other things that we've been working on the DXT side, on the Darshan side as well, is this idea of connecting back the recommendations that we are providing in Drishti with the location in the source code that originated that. So for that, we had a student working on this functionality. We have a pull request on Darshan to enable this kind of cross-layer exploration and tying back to the source code, where besides pointing the issue that in this case for MREX, the application is issuing 10% of all IO requests, all write requests are being small to a specific HDF5 file, we actually see where that is coming from the code so that the user might be able to make some changes to provide some performance improvements there. We also have the recommendation. Can you still hear me?
Yeah, now we can hear you.
Okay, sorry for that. Let's see. Okay. So besides that, we do provide this kind of general snippet so that the user can see how it could implement such techniques. It's not yet using the information from the source code, so it's not a specific recommendation for that application, but rather a general overview of how you could possibly fix the issue. So again, we're guiding, we're not providing the full solution to the user. So some key takeaways. The idea of Drishti was to detect the root causes of performance bottlenecks based on metrics coming from different levels of the IO stack, different sources of biometrics from different tools, map those into bottlenecks and provide recommendations. The way that Drishti does that today is using over 30 triggers that are kind of heuristic based. We're working to expand that into more complex set of triggers. And we have extended the support with collaboration with different students for ingesting not only Darshan and DXT logs, but also recorders, RP, and TOP. And with the combination of using the HDF5 Vault connector for Drishti, we can enhance the visualization side with the HDF5 related metrics so that we have this kind of full view of the entire IO stack. And with that, I'm open for any questions or suggestions you may have. You can also reach out to either myself or Strand through email. And thanks for listening.
Right. Thank you. Good question. One question.
So in that first graph you showed, we were using, the first graph was not in the collective metadata and the second one was. So your goal then is to somehow tell the user that you should be using collective? I mean, how do you envision doing that? I mean, if you have a database that says, I mean, how are you going to know to recommend that you use collective for the HDF5 side?
So if I understood the question correctly, in this particular case, we don't have like a database of expected patterns or how they would perform in the system. As I mentioned, it's more of a heuristic based. We know that for a given scale, if we detected that the application is using MPI, we're suggesting that the user tries to use collective operations as they demonstrated performance improvements in the past. From the HDF5 side, the difference here is that without the visualization, and this is a problem that we encountered when we first created Drishti, there was an internal issue with HDF5 that despite you asking the operations to be collective, the HDF5 library wasn't actually doing the request collectively. So in a sense, the user asked for something, but the system, the overall stack was doing something else. So without this kind of visualization to show this is what's actually happening, and these are some of the problems that you might want to tackle to improve the performance, it becomes hard to optimize the application. So again, the suggestions are kind of generic in a way, but based on previous works we have in the HPC IO field that pointed out to some of the best practices and some of the behaviors that applications could do that will harm the products. I'm not sure if I answered the question.
Yeah, thank you, Chandrakan.